Hey kids, time to learn some more derivative rules. This time in your notes, you want to title your notes Derivatives of Inverse Trig. So some things to remember about inverse trig from your prerequisite classes. In calculus, we are only interested in the inverse trig functions. And what that means is if I give you the function y is equal to the inverse sine of x, right? I am asking you about which angles have a sine of x. So for instance, if I say, who has a sine of 1/2, you know from your unit circle past history that on your unit circle, any coordinate on your unit circle, remember, and sine goes with y, this angle of pi over 6 has a sine of 1/2. Let's call it. Say this is theta right now, just to keep our variables straight. But I can also, right, because sine is positive over here, right? That breaks function rules. One input gives me two outputs. I can't have that situation. I have to have, for a function, I need to be able to put in 1/2 and only get one value out. So between quadrants 1 and 2, quadrant 2 lost. Quadrant 2 doesn't exist for inverse sine. If I ask you who has a sine of negative 1/2, well, that could be whoa, that's terrible. That could be 11 pi over 6, right? The y coordinate of that is negative 1/2. And the same over here with 7 pi over 6, the y coordinate of that. I can't have that situation because I want a function. One input has to give me only one output. Quadrant 3, lost. So if you want to know the inverse sine of negative 1/2, it's not 11 pi over 6 either. Because I want you to notice how I need to get, remember, I have eliminated quadrant 2 and 3. They don't exist. So if I want to get to 11 pi over 6, I have to start from the initial position and travel around my circumference, and I can't get any further than that, right? My domain stops. I can't go through quadrants that don't exist. So I have to go this way. Coterminal angle. And of course, that's 30 degrees and negative 30 degrees. And if you don't believe me, into your calculator, right, put yourself in degree mode just so you recognize what's happening. So you go to mode, go to degrees, and ask it for the inverse sine of 1/2. It gives you 30. Ask it for the inverse sine of 330, which is all the way over there in the fourth quadrant, and the calculator would tell you undefined. But if you ask for the sine of negative 30, sorry, negative a half, it gives you negative 30. It will not give you 330. I didn't mean to input 330. Sorry, I misspoke. All right, so those are, I could do the same argument for cosine. You need to know that inverse trig functions are defined this way. Quadrant 1 and 4, inverse cosine is quadrant 1 and 2, because here's where you get positive values. Quadrant 2 is where cosine is negative. You pick one quadrant. Quadrant 1, sine is positive. Quadrant 4, sine is tangent is the same as sine, except you just have to worry about the boundaries because if you have undefined issues. And then the reciprocals kind of do the same thing, except for, again, you got to work with boundaries. These are the ones you need to remember. Okay? So that was a little bit of background information. Now we're going to go to derivatives of inverse tangent functions. So look at what I've drawn over here. The blue function is sine x, but it's only from pi over 2 to negative pi over 2-ish. Pi over 2 is not exactly 1.5, but it's close, right? It's 3.14 over 2. That's quadrant. 0 to pi over 2 is through quadrant 1. 0 to negative pi over 2 is quadrant 4. So I have only caught a 1-to-1 piece of sine. The green line is y equals x, because the number 3 fun fact of inverses is that all the graphs of inverses are symmetric across y equals x, because the number 1 fun fact about inverses is that you just switch x and y. Okay? That red equation is the inverse of sine. But we usually like to get sine by itself, right? I'm sorry, we usually try to get y by itself. So I'm going to use implicit differentiation to figure out the rule for inverse sine of x. So the first thing I'm going to do is use the fact of what inverse sine of x really looks like, right? It's really x is equal to sine y. Switching. Then I'm going to take the derivative with respect to x of both sides. But remember, if you're taking the derivative with respect to x, but this is y, you have to chain rule that. And you think of y as holding a place for x stuff. The derivative of sine is, yeah, cosine of the stuff, spit out the derivative of the stuff. And then on the other side, the derivative of x with respect to x is just 1. Now, how do I get dy dx by itself? Yeah, right? This feels like implicit differentiation, doesn't it? Now I'm going to take a little side trip for a minute. And normally when we end up with implicit differentiation, we get dy dx by itself, and we just deal with the fact that we've got a y in there. Well, I really want a rule, an explicit rule for the derivative of inverse sine. So I'm going to go off into trig land, and I'm going to try to find a way to get rid of that y. Okay, so be careful. So this is going to be a little bit of a stretch here. You ready? Go. Sorry, this was just reminding you of where I got. Now I'm going to stop. Here's our trig identity. Hello, Pythagoras, right? This is our Pythagorean identity, the equation of the unit circle, right? Sine squared plus cosine squared is equal to 1. And I just put a y in there because remember, y is what I'm after. Got cosine squared by itself. And now I took the square root of both sides. Now when I take the square root of both sides, I take plus and minus, but I'm going to drop the minus because remember, cosine is only defined. We talked about, I'm sorry, being defined for inverse sine between negative pi over 2 and pi over 2, right? Now look at what I did. I have an expression for cosine y, and I just replaced this entire denominator with something that was not nearly as attractive. And it doesn't look like I've done anything. Look, I have a y here, and I still have a y here. So it doesn't look like I have gone anywhere. But I want you to look up towards the top there. Bing, 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 bing. X is equal to sine y, right? Because we switched x and y. Well, what if you square both sides? Oh, snap. Whee! That you got to write down in your notes. Excuse me. This is the derivative of inverse sine of x. The derivative of y when y was inverse sine of x. So notice that while I do have to deal with the fact that the derivative of inverse sine is a fraction, and gosh darn it, it has a radical, at least I don't have inverse sine. Taking the derivative of inverse sine got trig out of the situation. So here is all the rest of them. So you might want to pause the video while you copy all these down. Right? I could use the same technique to find, oops, where do I go? Inverse tangent, inverse secant, inverse cosine. I don't know why I left off inverse cosine there, but all of them. Oh, I know why. Taking the derivative of inverse sine is a radical under a fraction. This is the chain rule, right? This is the stuff. So it's 1 over the square root of 1 minus the stuff squared, spit out the derivative of the stuff. Inverse of tangent is a fraction without any radical, and it's a plus, so it doesn't matter the order which I add in the denominator. Notice here, not only do I have to have a radical, but I have to remember the stuff squared comes after the 1. Stuff, spit out the derivative of the stuff. Inverse secant is the worst, right? It's a fraction. It has a radical. I have to remember the stuff squared is before the 1, and the 1 is then minus 1. Plus, there's this absolute value of u thing on the outside. Oh, my Lanta. That's the worst. Now, here's the reason why I said I could use the same technique to find tangent and secant, and I kind of ignored the rest. Can you see the relationship between these three? You really only have 3 formulas to memorize. The derivative of inverse cosine is exactly the same as inverse sine, but negatized. The derivative of inverse cotangent is the exact same thing as inverse tangent, but negatized. OMG. And that's because of our shifts, right? Our trig functions are periodic and they're beautiful. So, right, I just can take inverse cosine is the same as inverse sine with a shift. Cotangent is the same as inverse cotangent with a shift. And guess what the derivative of tangent with a constant is? Right? All right. So let's do some examples. This one is straight up, right? I just need a formula. There's no stuff. I just have to remember, oh, inverse sine, right? Because the inverse trig formulas are kind of down on my list and my things that I memorize, right? I got those power down rules. I got the regular trig rules, got my chain rule, my product rule, my quotient rule, right? Inverse trig is kind of down on my list. So I have to think inverse sine. Okay, it is a fraction. They all have 1 in the numerator. Sine is the positive one. Remember, it's only the C ones, cosine, cotangent, cosecant, that begin with a negative. Inverse sine has a radical, and this was 1 minus, right? 1 minus the stuff. Oh, there's no stuff, so it's just x squared. And I don't have to spit out the derivative of x with respect to x because that's just 1. But they want me to know what is the derivative at 1/2. Now, if you have a calculator in your hand, don't you dare even worry about the formula. You're putting inverse sine into y1, and then you are math aiding with, right, 1/2. You are not doing any calculus. You don't have to rationalize that, right? Unless multiple choice does. And multiple choice, I have to say, is kind of like 50-50. Sometimes they rationalize denominator, sometimes they don't. All right, that was slow. Let's do another one. How about trying that one? See if you can do that one. Probably maybe pause the video for a second. This time I do have stuff, right? So I'm using the same formula. 1 in the numerator, radical in the denominator, 1 minus the stuff squared times the derivative of the stuff. Okay? Done and done. Let's try some more. And again, if you want to pause the video and try these on your own, I do actual no calculus on this first, but I recognize that I have stuff. Inverse tangent is a fraction without any radicals. I like inverse tangent. I'm not supposed to have favorites, but if my inverse trig, inverse tangent is my favorite. Yes? Now that would probably in multiple choice look like this. What if I asked you about this at x equals 16? One over 2 times the square root of 16 is 4. 1 plus 16 is usually 17. So whatever 8 times 17 is. 136 maybe? I don't know. Check my math on that. Oh, the worst. Boo. I don't like inverse secant. I've got stuff. S, so I'm positive. Got a square root. Who goes first? Let's see. Inverse sine is 1 minus. So this is right? Right? No, nope, nope, nope. What did I forget? I wrote this for a reason. What did I forget? Inverse secant has that gosh darn thing out front. Now, this is perfectly fine as an answer, but here's something that might happen to you in multiple choice, right? That's the absolute value of 5x to the fourth. But what's true about the absolute value of 5? Right? It's 5. And what's true about the absolute value of x to the fourth? It's always positive as well. So it could be that AP in multiple choice does this. Again, you don't have to do this unless you're matching multiple choice. And then, of course, some things cancel out there, right? Okay. All right. So we will do a couple more examples in our live sessions. But for now, we will see you then. Take care.